Herewith, I am going to discuss the transformer test which are needed to find out the equivalent circuit parameters and compute the performance measures such as voltage regulation and the efficiency likewise. So as mentioned, this particular is the equivalent circuit. With the help of the test, we can find out the resistance and the reactance of both primary and secondary winding. We can find out the shunt branch parameters Rm and Xm with the help of test. The tests are used to find out the core loss and the rated full load copper loss PCUFL. So with the help of these two losses we can calculate the efficiency. Likewise, the other measures such as the maximum efficiency etc. can also be calculated. We can obtain the voltage regulation as well. Let us take one example. With the help of this example, much clarity will be thrown on the various aspects of the experimental procedure of the test. This particular distribution transformer has a typical rating of 220 kVA, 11 kV, 440 volt. So let us calculate the current level on both sides. This will be able to help us in identifying which side will be our preference for experiment and why. So the currents are calculated as on the 11 kV side, which is a higher voltage, that is 20 ampere. On the 440 volt side, which is a low voltage, the 500 ampere. So let's say the 11 kV is a high voltage. In comparison, the 440 volt is a low voltage. Similarly, the 20 ampere is a low current in comparison to the 500 ampere. So it is easily, you can say it will be safe if the choice is given to work with the 440 volt instead of the 11 kV and the 20 ampere instead of the 500 ampere. So this particular suggests if the rated voltage is the consideration, we shall be connecting the measuring instruments on the low voltage side. Similarly, if the rated current is the consideration, we shall be connecting the measuring instruments on the high voltage side. Now that particular is one aspect. The availability of the instruments, availability of the supply is also another consideration, because the 11 kV is a great, or you can say the significantly high voltage, and that particular voltage is normally not supplied to the typical residential area, or you can say the laboratories within the premises of academic institution. Now other aspect here which we need to have in mind, that the windings are rated with the high voltage HV or the low voltage. So they are normally not rated as primary and the secondary, which we have been using as a terminology to build the equivalent circuit parameters. This particular has already been highlighted, that the test has to be carried out in such a manner keeping the availability of the measuring instruments, supply and the safety aspects. So the two tests are carried out, which are the open circuit and the short circuit tests. These tests are sufficient to give us the detailed information about the equivalent circuit parameters and the performance measures which we discussed previously, such as the efficiency and the voltage regulation. The open circuit test or no load test. So this is carried out at the rated voltage. The low voltage is the choice in comparison to the high voltage. So all the measuring instruments are connected on the low voltage side, where say the high voltage side is kept open circuited. Now this is carried out at the rated voltage, so this is pertaining to the LV side rated voltage. This is the no load, so only the magnetizing, or you can say the no load current is drawn. So this no load current is giving us the information about the core losses and the magnetizing branch parameter Rm and Xm. So we have to take care that Rm and Xm, which we will be evaluating, are pertaining to the low voltage side. This is the equivalent circuit when say there is open circuit at the low voltage side. This reduces or re-represented likewise. Now the no load current I0 is only about 5% of the rated current, that is one aspect. The winding resistance and the leakage reactances are kept small to have a good, or you can say high efficiency and so on. So the voltage drop because of this no load current in this series winding elements, winding components can be eliminated. That reduces this to the level like this. So with the help of the three measurements, that is pertaining to the voltage V0, current I0 and the power P0, we will be able to calculate Rm and the Xm likewise. So this particular, you can easily have a diagram here, that this voltage is supplying the current I0, which is resolved into the two component IC and IM. So first let's see the phasor diagram. Because I0 is predominantly reactive, so this particular I0 angle with V0 will be about 75-80 degree or so. Under the ideal condition, it has to 90 degree coincide with the IM. This I0 is resolved into two component IC, which is the in phase component, and IM, the quadrature component. So the power, real power will be V0 IC. That particular IC is nothing but I0 cosine of theta 0. Using this you can find out the IC likewise. IM can be obtained in this particular manner, or you can make use of the I0 sine of theta 0. So with the help of that, Rm, which is V0 upon IC, and Xm, which is equal to V0 upon Im, can be calculated. So this particular can easily be correlated with this circuit diagram like this. But the point which we have to remember, that these Rm and Xm are referred to the low voltage side. So when say we are having an equivalent circuit, the equivalent circuit can be obtained referred to the low voltage side, or can be obtained referred to the high voltage side. So when say these particular parameters are to be referred to the high voltage side, they are to be multiplied by the turns ratio square, where say the turns ratio is nothing but voltage of the high voltage side, rated voltage of the high voltage side to the rated voltage of the low voltage side. So that particular ratio is defining the turns ratio. Now the short circuit test, it is the other test. It is carried out at the rated current. So that particular rated current is the full load current. But please be mindful that this full load current is pertaining to the high voltage side, because that is having a low current value. Now keep in mind that this is to be carried out at rated current, while say the secondary or the low voltage side is kept short circuited. So here say we will be using the thick wire, because very heavy current will flow on the low voltage side. Now this is the similar arrangement for the power and voltage measurement. Only thing here is that this auto transformer usage is must, because the test is to be carried out at the rated current. So that rated current is achieved at very low voltage in comparison to the rated high voltage side voltage. So that voltage level is coming out to be about 5 to 6% of the rated high voltage side voltage. So we will be gradually varying the voltage until the rated current flows. Now this particular is giving us the full load copper loss likewise, but the point is to be remembered that the measurements and the parameter which will be obtained will be pertaining to the high voltage side. So the equivalent circuit will look like this. Now as say the short circuit test is performed at the low voltage, So because of this, the no load magnetizing current component will be much smaller. The core losses will also be negligibly small. So you can neglect the I0, and when say that is neglected, it reduces to the likewise. So this R1 and R2, they are basically the R2 dash, they are pertaining to the high voltage side. Similarly, the X1 and X2, they are also pertaining to the high voltage side, can be evaluated. So RSC and JXSC we will be evaluating with the help of PSC, ISC and VSC. ZSC is evaluated likewise, that is the voltage divided by the current. Similarly, this is a series element, so ISC, I square R analogy is given to calculate the RSC, then the XSC is evaluated likewise. Once you are drawing the phasor, you will find that under the short circuit, the transformer is behaving like, say, predominantly reactive or inductive. These parameters are calculated at the high voltage side. So if we have to refer these parameters to the low voltage side, the appropriate adjustment with the turns ratio square has to be carried out. So here say this is the procedure for separating the winding resistance and the reactances. Because we have to separate the resistance, so that particular is only possible when we are knowing one of the winding resistance. So let's say the DC resistance of the HV side winding is measured as this. So this measurement can be done by the DC load test or by the multimeter arrangement. As say the transformer is the AC arrangement, so this DC resistance is reflected as AC resistance simply by multiplying by a factor of 1.2. So that is giving the RHVAC, and that we are saying the RHV. Now you see that the equivalent resistance on the high voltage side will be consisting of RHV and the transformed low voltage side resistance. So once say the RHV is known, RLV dash can be evaluated as RSC minus RHV. There is no procedure to separate out the leakage reactance, and that particular precise information can only be supplied by the manufacturer. So we will be equally dividing the reactance on both the sides. So that's why the XHV is taken as equal to the XLV dash, and that particular value will be XSC by 2. Now when say we have to refer the parameter of this particular parameter on the low voltage side, you have to divide by the you can say the turns ratio square, where say the turns ratio is defined as V rated HV upon V rated LV. So this particular is a summary of what has been discussed previously, and the parameters are, you can say, when say the transform parameters are used, the exact equivalent on either side can be obtained. There is no problem as such. When say we are referring to the high voltage side, then RHV and XHV, they are say the parameters available by the direct measurement. These are the transform parameters we will be utilizing. When say it is a equivalent circuit referred to the low voltage side, so the magnetizing branch parameters are used as it is. Others we will be utilizing after having a transformation and so on. This is the example. So in this example, the 20 kVA 2000 volt, which is a high voltage, 200 volt, which is a low voltage transformer is used, and the test data is given. You please see that this open circuit test is to be carried out at the rated voltage. So this 200 volt is coinciding with the low voltage side as mentioned in the previous discussion, and short circuit test is to be carried out at the rated current. So this test measurement is coinciding with the rated current at 2000 volt level. Thereafter we have to calculate the parameters and draw the approximate equivalent circuit as asked. So the low voltage side data, with the help of that we will be calculating the IC, which is the P0 upon V0. Once a IC is known and the I0 is known, so you can calculate the IM. Once the IM is known, you can find out the value of RM, which is equal to V0 upon IC, and XM, which will be equal to the V0 upon IM. Here you can easily make a comparison that the XM value is coming out to be lower than the RM value. So the magnetizing current is high here, or you can say because of the high magnetizing current, the XM value is low. Another aspect, the RM value, which is a shunt parameter, has to be kept high to have a lower amount of the core losses. The turns ratio is available, so you can find out the transform parameter referred to the high voltage side simply by multiplying by the A square term. On the short circuit test side, we are having a measurement of the PSC, VSC and ISC. This particular is coming out to be a series arrangement. So you can calculate the RSC simply by PSC upon ISC square. ZSC will be the VSC upon ISC, and the XSC can be evaluated likewise root of ZSC square minus RSC square. When we have to refer the parameter towards the low voltage side, they are to be divided by the turns ratio, and it is done. Here say we have to find out the approximate equivalent circuit, so there is no point in separating out the winding parameters between the high voltage and the low voltage sides, and the approximate equivalent circuit can be drawn it likewise. So only adjustment here, when you are referring to the high voltage side, these particular RSC and XSC are available directly, whereas the magnetizing branch parameters are the transform parameter. While say you are using the approximate equivalent referred to the low voltage side, these particular magnetizing branch parameters are available with the help of test. Other parameters are to be transformed, or you can say the transform parameters are to be used. So with this we can have a summary that the open circuit test is carried out on the low voltage side to obtain the core loss and the shunt branch parameters. Short circuit test is performed at the rated current on the high voltage side to get the full load copper loss and the equivalent winding resistance and the reactance. So these particular will be pertaining to the high voltage side. In obtaining the equivalent circuit, we have to have a care to transfer the parameter from one side to the other side using the turns ratio square in the appropriate manner. For further reading, you can refer these textbooks. So thank you.